All right, welcome to probability lecture 2, tree diagrams. So tree diagrams, very helpful way of looking at conditional probabilities. With conditional probabilities, we really need to make a tree diagram because a Venn diagram is about ands and ors, and a tree diagram is about one condition leading to another condition, or an unconditional leading to a conditional. So for men, binge drinking is defined as having 5 or more drinks in a row. Women as having 4 or more drinks in a row. The difference is because the average in weight. According to a study by the Harvard School of Public Health, 44% of college students engage in binge drinking, 37% drink moderately, and 19% abstain entirely. Another study reported that 17% of binge drinkers are involved in an alcohol-related accident. Of binge drinkers. That means that is a conditional. Since that is a conditional, all right, that's what indicates we have a tree. And it's not just that one. Of those that drink moderately, 9% are involved in an alcohol-related accident. And those that abstain, 2% are involved. So we see lots of conditionals. So the question says, create a tree diagram. And we can identify our info while simultaneously creating this tree diagram. Probability of binge drinkers, 44%. Probability of those that drink moderately, 37%. And probability of those that abstain, which I'm actually going to call N for no drinking, since my second conditional is an alcohol-related accident. I'm going to use A for that, 19%. Then, of those that binge drink, 17% are involved in an alcohol-related accident. That means that branches off of those that binge drink. Accident given binge drinking is 17%. Similarly, of those that drink moderately, the probability that they're in an alcohol-related accident is 9%. And then of those that do not drink, only 2% are involved in an accident. So each set of branches sums to 100%, which means that's 100%. This one needs to be 100%, and this one needs this one and this one. Each of those all need to be 100%. So I can do this just by doing complement. If that's 17, that makes this 83. Similarly, no accident given moderate drinking is 91%. And lastly, no accident given no drinking is 98%. Then we're going to create what we call the simple events. Now, each of these branches lines out as the probability of B times the probability of A given B. That actually creates the event A and B. And that's what a simple event is. Something without a conditional. Similarly, A and, or not A and B, and A and M, and not A and M. That creates our list of all the simple events. Then we want to make the associated probabilities. So and means multiply, which means all I have to do is multiply these values. And again, 4 decimals, we want to be in 4 decimals because when we convert that to a percentage, that still has 2 decimals, which is basically common sense standard rounding. Okay, so once we do all that multiplication, we also notice that all these values sum to 1. All right, so all the values here sum to 100%, as well as that sums to 100, that one sums to 100, that one sums to 100, and all of these sum to 100. It's basically a logic check as you go through the problem. If you can identify that each of the branches sums to 100%, then your values at the end should also sum to 100%. All right, so then we can answer all kinds of questions. Setting up the tree diagram is the biggest thing, and identifying that we have a tree diagram is a big thing. All right, now good news, initially I'm always going to say create a tree diagram. All right, so on the first quiz, I'm always going to say create a tree diagram. If it doesn't say create a tree diagram, then you're probably, doing a Venn, or you have a table or something else. All right, so the second question, find the probability of being in an accident. So probability of A. In order to find that, you go back to your simple events, and this is basically all you use. After we create the tree, we actually don't use the tree anymore. From here on out, we only use the simple events and those corresponding probabilities. If I'm looking for a probability of being in an accident, that means I need to sum up everything with an A. There's an A, there's an A, and there's an A. And that gets us the probability of being in an accident. And in this case, we mean alcohol-related accident. Lastly, suppose the student has never been in an accident. Find the probability the student was a moderate drinker. So this is another given. Suppose, all right? That is a subtle way of saying given. Suppose the student has never been in an accident. Given the student has never been in an accident, find the probability they were a moderate drinker. Then we use our definition of conditional probability, which is the joint M and not A divided by the probability of not A. M and not A we have on our picture here, 33.67%. And then not A, I actually just found A in the part above here. So not A is 1 minus that number. Which gives us, all right, our completed solution. So another big thing we like to talk about are odds. All right, odds is just another way of identifying probabilities. With probabilities, all right, we're very familiar because it's the number of possibilities out of the total. Odds is more along the lines of possibilities something does happen versus possibilities something does not happen. So probability, all right, something simple, odds of rolling a 4 on a fair die. The probability of that we're very familiar with, right? Roll of 4. One possibility out of 6 on a normal standard 6-sided die. The odds, notice, right, are represented as there's one possibility that does happen and 5 possibilities that does not happen. Notice that those two numbers together sum the denominator. All right. And in order to do odds against, you flip it. It would be odds against rolling a 4 is 5 to 1. Let's look at another example. And the best way to usually go about odds is start with what we're most familiar with, which is probability, and then turn that into odds for, and if the question asks, flip it to find odds against. So the winner of a raffle will receive a 2-year scholarship to the college of his or her choice. If 1,000 raffle tickets were sold, you purchased 5 tickets. What are the odds against your winning the scholarship? So let's start out with the probability of winning the scholarship, which is 5 out of 1,000. Now, I typically don't reduce my values except, all right, when we're about to convert to odds. Odds always want to be in the lowest terms. So I am going to reduce this to 1 out of 200. So the odds for this, all right, there's one possibility you win the scholarship and 199 you don't. All right, because again, 1 plus 199 makes our denominator, which is 200. The odds total all the possibilities that can happen. And since we were actually looking for odds against, all we have to do is flip it. 199 against to 1 possibility for. So drawing without replacement. We talk quite a bit about probabilities, and a lot of times we kind of assume we have this infinite number, right? We don't change the probability as we calculate things. Without replacement is when you have limited sample size. The most common is a deck of cards. You know there is only 52 total cards. So with odds for, it's important to make sure that you adjust the numerator and the denominator. So let's look at pick 2 sodas at random without replacement from 2 Cokes and 3 Sprites. It's always going to be very clear that you're drawing without replacement. It will say without replacement. Otherwise, we pretty much, unless it is a very, very limited sample size, we pretty much assume that we're drawing over and over. So if you select a Coke, all right, if you initially select a Coke, what is the probability your second soda is a Sprite? So initially select a Coke. So there were 2 Cokes. So basically probability Coke on first pick. That probability is 2 out of 5 total sodas. But after I initially select a Coke, that means I'm down to only 4 sodas. What is the probability that your second soda is a Sprite? So probability second is a Sprite given first is a Coke. So I know that I'm down to 4 sodas, all right? And the first one was a Coke, so there are still 3 Sprites left. Now, I could create a tree diagram to identify this, but sometimes with limited enough sample size, we can basically just kind of think that out, all right? We can just go through the logic of that. And then what are the odds against part A? So again, now let's do odds for. There were 3 possibilities that does happen. 1 it does not. So hence the odds against are 1 to 3. And basically that's how you approach odds every time. All right, false positive and false negatives. This is one of the most important concepts that have come up, all right, I mean, it's always been a big deal, but it's really come up heavily since COVID, all right? What is a false positive and what is a false negative? So, always good to look at an example for it. given disease like tuberculosis, TB, I want to investigate this with a tree diagram discussing false positive and false negatives. So a false positive, and this is in any case, all right, it's when a healthy person gets a positive result. So in this case, someone without TB gets a result of TB. A false negative is when a sick person gets a negative result. So in our TB case, when someone with TB gets a result, they do not have TB. So according to the CDC, the incidence of TB in the United States is 3 cases per 100,000. All right, and these are true statistics. I always try and use true statistics. TB is an uncommon disease. Additionally, TB can be a matter of serious concern. So the test claims to correctly identify 99% of people who don't have TB. The TB test also claims to have a false negative rate 10 times better than the false positive rate. So, why is it important to have a false negative rate much lower than a false positive rate? This is very, very common for almost all tests. You want a false negative rate much lower because you don't want to tell someone that they are not sick when they actually are, especially something like COVID, TB, etc. Because if you think you're fine, you don't do anything about it and likely then go spread the disease. So you want a very low false negative rate. What that results in is usually a higher false positive rate, which is why so often tests have higher false positive rates, and you always should take the test again, all right, to make sure it was not a false positive. So can we think of another example when we want lower false negative rates than false positive rates? Yes, absolutely. The most common, we just saw them, COVID, all right, any disease. And another one, pregnancy. You don't want someone out there thinking they are not pregnant when they actually are, because they could be drinking, they could be taking riskier behavior. All right, so we almost always want lower false negatives than false positive rates. All right, when it comes to disease, that's always the standard practice. However, can we think of an example when the false positive is worse than the false negative? And the answer is yes, the justice system. All right, the false positive rate actually means that you're sending an innocent person to jail. The false negative rate is letting a guilty person go free. Now, be aware, neither of them are good, all right? But the criminal justice system is defined as guilty beyond a reasonable doubt. So we like to make sure that that person is absolutely guilty, all right? And so we let many guilty people go free, the false negative, all right, in order to avoid basically ever having a false positive in the justice system. All right, back to the problem. So what percent of people test positive for TB? What is the chance of having TB after a positive test? So this one said above here that we wanted to investigate this with a tree diagram. In order to do that, though, we first need to pull out our information. This had a lot of detailed information and it wasn't presented in a standard way. So we know the probability of TB is 3 cases out of each 100,000. I could similarly find the probability of no TB, and we'll do that in a bit. Additionally, and here's how these tests, basically the information is always given. The test claims to correctly identify 99% of people who don't have TB. That means they correctly identify those who do not have TB. That means given we do not have TB, it is correctly identified, and the correct identification for that is a negative result. Hence, all right, if I know the correct identification, that means the false positive which is the probability of getting a positive result given no TB, is 1%. And these are always read as correctly identifies, correctly identifies those who don't have it, or correctly identifies those who do have it as some percentage. And that's basically how most tests state their probabilities. So they state the opposite of what the false positive or false negative are. So this one also tells us, right, and they say this often as well, the test claims to have a false negative rate 10 times better than the false positive rate. Okay, so we identified the false positive. So the false negative which is the probability of a negative result given I do have TB, is 10 times better than the false positive rate. So this 0.01 has to be involved. But now here's the thing, 10 times better. Okay, that doesn't mean we multiply by 10. Okay, because this number here would become bigger. It's actually you divide by 10. That's what is 10 times better when it's referring to false positive and false negative results. So we have almost everything. One last result. Probability of getting a positive, given we actually have TB, is 1 minus 0.001, which is 0.999. And the trickiest part of this is actually identifying the information, and it's always because how information is given when it comes to false positives and false negatives, all right? And how they always claim tests do, right? Correctly identify 99% of people who don't have TB, all right? So always write out that conditional, right? Given you don't have TB or whatever, all right, chance of positive. Well, now we have all the information. Now we can actually make a tree diagram. All right, so probability TB is 0.00030, one more zero. 4 zeros. And then hence probability of no TB, 0.99997. Now, I know I was talking about 4 decimal rounding, but we have very, very small numbers. All right, so it's always better to be more precise, and especially 3 out of 100,000 ends up as a very small number. And so we want to just be as precise as possible here. All right. Contextually, most of the time we round to 4 decimals, but if the problem demands it, you need to go to more decimals. And then we use all the information we identified above. All right. Negative given no TB, positive given no TB, negative given TB, and positive given TB. So probability, positive, given TB, 0.999. Probability, negative, given TB, which is our false negative, 0.001. All right. And then this allows us to do the simple events, SE. So TB and positive, TB and negative, TB and positive, TB and negative. And lastly, the probabilities. All right. So Since these numbers are very, very small, I'm not going to write them out all the way, but each of these, right? So I'm doing 0.00003 times 0.999, all right, to get the resulting value here. And I'm just going through each branch, all right, to get its corresponding probability. And since the numbers are very, very small, 0, 0, 0, 0. Whoops. All right. So, all right, we have our tree completely filled out. All right, we only have four simple events here and their corresponding probabilities. And again, this does sum to 100%. I mean, this last value is about 99, and the rest of them are basically 1%. So then we can answer questions. What percent of people test positive for TB? Or whatever that was, D. So probability positive, which is just the probability of positive and TB plus the probability of positive and no TB. And again, yeah, we're going to like 8 decimal rounding here just because these values are so small. All right. And lastly, what is the chance of having TB after a positive test result? That means, again, that is a conditional. Notice it doesn't say assume, suppose, of any of that. Chance of having TB after a positive test result. That means the positive test result came first. That is the given piece. So probability of TB given positive, using our definition of conditional probability, TB and positive divided by the probability of positive, and TB and positive, which actually we have above, and the probability of positive, which we just found as well. All right, so what that says, right, is even if you test positive, all right, you're still, there's only a 0.3% chance you actually have TB. All right. And this is the point all along. And this is true for many of the more rare diseases. The higher incidence of the disease, the higher this value would be. All right. But, all right, false positives happen all the time. And so the entire point is take the test again. All right. It's still very, very unlikely that a positive result actually means the truth. All right. Because false positives are so much higher, all right, with testing than false negatives. If you get a negative result, ideally you can trust that, but you should always double check, all right? False negatives are much, much lower, but they still occur as well. All right, and then just a couple of notes. What can go wrong? All right, don't confuse disjoint with independent. Those are two separate ideas. All right, we've really investigated those pretty heavily, and we want to make sure that you keep those separate in your mind. All right, watch out for something when it says without replacement, and don't use the simple rules when complicated rules are required. All right, have yourself a wonderful day. Thank you very much.